So let's start with the simplest truth table for negation. If we have a proposition P, then the negation of P is false if P is true, and the negation of P is true if P is false. So here you could see that we have a truth table of size 2, that's 2 to the 1, the number of proposition you have. So we're working on only one proposition, negating it, so that the size is 2 to the 1. And the function that we are building is actually the function negating P, which is equal to false or true depending on the value of the truth table, of the proposition P. How about conjunction? Conjunction creates a new compound proposition based on two propositions. So given two propositions P and Q, the compound proposition is P and Q, and will depend on the truth value of P and Q. So the size of the truth table is 2 to the 2, which is 4, because we have two propositions that we are putting together through the conjunction. All right? So the semantic of the conjunction is as follows. If P is true and Q is true, then the compound is true. If P is true and Q is false, then the compound is false. If P is false and Q is true, then the compound is false. If P is false and Q is false, then the compound is false. In other words, the conjunction P and Q is true only when we have both propositions are true at the same time. If we think about, for example, the 1+ word, we're going to have 1+ in 1, 2, and 1+ in 2, 1. This is a false proposition because we have only one 1+, and we can't have them both in two cells. So we must have one of them false. So if any of them is false, we are actually having all of the outcome of the compound of the conjunction is being false. All right. So now the disjunction. Disjunction is similar in terms of truth table. We also have here 2 to the 2 because we have two propositions. But for the disjunction, we are going to have the disjunction weaker than conjunction in the sense that whenever we have any of the proposition true, we have the outcome to be true. If both propositions are false, then we will have the outcome to be false. If, again, I take the proposition 1+ in 1, 2, or 1+ in 2, 1, means that it's enough to have a 1+ in one of the two rooms to have actually the proposition 1+ in 1, 2, or 1+ in 2, 1 to be true. Exclusive OR is another useful connector that actually is true only when, whenever there is only one of the propositions true. As an example of this, the exclusive OR, you could think of if you go to the restaurant and you have on the menu soup or salad coming with a meal. So you can't expect to have both of them. So you expect to have at least one of them, right? But you can't expect to have both of them. So you have either you have a soup and not salad, or you have a salad and not soup. Okay, so basically this proposition here, P exclusive OR Q, would be true only if you have one of them, exactly one of them, equal to true. So you can't have both of them, and you are ensured to have at least one entree coming with the meal. So again, here it's 2 to the 2. That's going to be the truth table for the XOR. Here's another important truth table, the truth table of implication. Given proposition P and Q, P implies Q will be false only when P is true and Q is false. So this is the definition that logicians decided to give to implication, in the sense that whenever the P is false, we give the implication truthfulness the benefit of the doubt. So we're going to have false implies anything. So the function will be true whenever if P is true, then and Q is true, then the implication is true. If P is false, whenever Q is true or false, the definition of P implies Q is true. So this is the only case where the implication is actually false. Bidirectional, or if and only if, noted as IFF, is a double implication. So it's P implies Q and Q implies P. So we have P and Q. P equivalent to Q is true only when we have both P and Q true or both P and Q false. So that's the main connectors in propositional logic. Just like in arithmetic, there is a precedence of operators for logical connectors. For example, expressions in parentheses in propositional formulas are actually processed from inside to outside. We first give priority to the negation if it is there, then the and, then the or, then the implication, the bidirectional or if and only if. Otherwise, we use left to right. Whenever you have a doubt, just use parentheses to express your proposition and avoid any confusion. We can build larger and larger propositions. For example, given the three propositions P, Q, and R, it's possible to build the proposition that's composed using connectors composing P, Q, and R. So for example, P or Q implies R is a proposition. This truth table is actually made of 8 n-tuples because we have 2 to the 3, given that we have 3 proposition symbols. Logical equivalence is another feature in propositional logic. Two propositions P and Q are called to be logically equivalent if and only if the columns in the truth table are actually identical. We write this as P equivalent, logically equivalent to Q, or P equivalent to Q. For example, if we take P and Q, we know that actually the implication P implies Q is logically equivalent to not P or Q. You could see that if you do the truth table for these two compound propositions, you're going to get exactly the same truth value for the truth table. So these two propositions are logically equivalent. They have the same truth value for any compositions of P and Q. So this is important. It allows us to transform propositions from one setting to another one. Just like in arithmetic, we have some properties on the operators. For example, the property of commutativity holds for propositional logic symbols. For example, P and Q is equal to Q and P. P or Q is equal to Q or P. But P implies Q is not equal to Q implies P, so be careful with that. Associativity, if you have P and Q and R, you could just change the order of the parentheses. Same thing for the disjunction. The identity element is true. For example, P and true is always P. P or true is true. So we have, remember the definition of the disjunction. Whenever we have one of the two elements in the disjunction is true, we have true for the compound proposition. Not P is P. P and P is P. P or P is P. We can distribute the conjunction over the disjunction and the disjunction over the conjunction. Also, P and not P is false, because one of them must be false, so the conjunction requires that both of them be true to be true. P or not P is true, because one of them is guaranteed to be true. We use an important feature called De Morgan's law that allows us to introduce the negation on some compound, conjunction, or disjunction. The negation of a conjunction is the negation of the first term or the negation of the second term. The negation of a disjunction is the negation of the first term and the negation of the second term. We also like to talk about tautologies and fallacies or contingencies. A tautology is a proposition which is always true. For example, suppose we have P. If I take P or not P, B or not to be, so this is true. We always have one of these two terms to be true, which means that the disjunction is always true. So this is called a tautology. We call contradiction or fallacy a proposition that is always false. Consider this one, P and not P. I am upstairs and downstairs is something that cannot be true at the same time. So we're going to have this false. It's a fallacy for any value of P. Finally, a contingency is a proposition which is neither a tautology or a contradiction. So it depends on different situations. So we'll have a mix of true and false in their truth value.